All right, good morning all. So today we embark on another new chapter in what we do, and the topic is going to be we'll talk about this thing called an operational amplifier. And so before I get into the lecture, I want to point out a couple things. One is that you're going to hear about two big words in today's lecture. Okay, two big and incredibly important words. Okay, and I want to mention those words to you right now so that when I come to them in lecture, you can say, okay, I better pay really close attention. These are important words, all right? So one of them is abstraction. And the second one is feedback. Okay, two incredibly important concepts. Abstraction you've been seeing a couple times during this course. Once in the beginning, where we abstracted out Maxwell's equations by focusing on a smaller playground and simply using KVL, KCL in place of those equations. That was a big abstraction. It turns out that almost all of EECS is based upon abstractions at various levels. In the first lecture, I also showed you the layer upon layer of abstraction that we build to be able to build interesting systems. The second big thing is feedback. Okay, and I'm going to relate this to anti-lock brakes in cars, and so you can wait and see how we do that. It's an incredibly important concept. Okay, so before we dive into the amplifier abstraction, let me first talk about something that you know. Okay, and start with something that you know, and then lead up into the operational amplifier and its circuits. So you know about the MOSFET amplifier. So the MOSFET amplifier that you know about looked like this. So it's based on a MOSFET. There's a VS supply. There was a VI input, a VO output, and as I said, a VS supply. So this was a MOSFET circuit that you've seen before. And in this, one way of viewing this is that this circuit has three major ports. Okay? This here is the input port with voltage VI. This here, between the drain terminal and the ground, is the output port. So I take the output between the drain terminal and ground. And finally, we have the third port, which is this one. It's called the power port. I apply VS between this terminal here and the ground terminal, and that gives us the power port. So this device here was a three-port device. Okay, input port or control port, output port, and a power port. And so we looked at the circuit and did a whole bunch of analyses of it. Then what I can do at this point, now that you've seen this, it's oftentimes interesting to think about abstracting this out into some kind of a building block. Okay, much like in software, you write a procedure and you abstract out the internal details of the procedure in the procedure declaration and in the call that you make. In the same way, we can take this little device here and abstract that out into the following abstraction. Okay, we can abstract that out as a device that looks like this. So I have my input port. I have my output port. And I have my power port. Okay, so I can apply Vs here. And notice that I've taken these 6 terminals here, 1, 2, 3, 4, 5, and 6, all right, and put a box around it and just expose the terminals to you. And I need to tell you a little bit more about the internal properties, but suffice it to say that you can begin working with this little block. And an even simpler version of this for many applications might just look like this. Vi and Vo, where there is a ground that is shared among them that's implicit in this picture. And Vi and Vo can simply be the node voltages at these nodes. So this is a progressively more abstract representation of this amplifier. So what we can do is, provided we know, we can abstract out the relevant properties of this block and expose them outside. And the relevant properties might well be that, let's say here, the properties may be that I in is always 0, right? I can also express to you the gain of this amplifier. I may also be able to tell you a Thevenin equivalent for the output. Okay, so there are some properties that I can give you that will let you use this building block abstractly. So today, what we'll do is introduce a powerful abstraction of a type of amplifier. And this is called the operational amplifier, okay, or op-amp for short. So, what I'm going to do is give you a slightly more involved building block than the one I've shown you there, but suffice it to say that the idea is going to be the same. So this building block looks like this. Okay, this building block has an input port. This building block also has a port in which to connect power, or the power port. And the way I'm going to connect power, I'm going to connect a plus Vs supply here. That's going to be my ground node. And I'm going to connect a minus Vs supply to this node here. Okay, so these voltages are both Vs. So I'm going to apply a plus Vs here and a negative Vs out here. And I'm going to take the output between the ground node and the output node of the operational amplifier, call that V0. This is the output port. So input port, an output port, and a power port. Okay, this is a bit of a, think of this as a pattern, okay, where I have an input port across which I connect the input. I have a power port across which I connect a plus Vs, minus Vs supply. And then I take the output terminal and take a ground terminal, which is defined by external components of my circuitry, and use this as my reference node. Remember, ground is just a reference node. I'm going to use this as a reference node. These two are equal in magnitude, and take this as my output. Okay? And when I do something like this, I can build an even simpler. So this is an abstract differential input amplifier. In other words, this amplifier is going to amplify whatever I apply at the input. So a slightly more abstract representation of this looks like this. V out and plus minus V in. Okay, this is a slightly more abstract representation where, remember, we're going to draw this again and again, maybe at least 38 or 39 times in this course. And remember, each time we draw it, remember that there is an implicit power port, a plus minus supply that is connected, which we don't show. Okay? And I remember when I first learned about it a long time ago, I was always, there was a confusion in me initially. So how does this work? Where's the power coming from? But just remember that power comes from a plus-minus supply, and we just don't show that in this abstraction. Okay? Now, the details, a lot of details are in chapter 16 of your course notes. That's a reading for that. The other thing is that there are some other key properties of this amplifier. Okay? And let me discuss those very quickly. So first of all, I can draw a circuit model for the amplifier. Make some room for myself here. And this is the circuit model for what we call the ideal operational amplifier. Okay? And the circuit model is going to look like this. Okay, this is an abstract device. And in terms of analyzing how this behaves in a circuit, I'm going to show you this abstract circuit that looks as follows. So some input V is applied at these two terminals here. And this terminal is called my V plus terminal. And this is called my V minus terminal. So this corresponds to these two terminals. I'm telling you that the current going in is going to be 0. So I plus is going to be 0. And I minus is going to be 0. So I plus is the current in here, and I minus is the current into the V minus terminal, and both these currents are going to be 0 in this device here. The output is going to look like this. The output is some, let me just call it V out to be consistent with this here, and taken with ground as my reference, and the output is simply AV. So in other words, what I'm doing is I'm going to model this as a device that has a dependent source at its output. And the dependent source here is a voltage-controlled voltage source. Okay, the dependent source, it's a voltage-controlled voltage source such that the output voltage is A times the voltage V across its input. Okay, so this is actually very simple. Think of these three terminals here I've shown you here. I apply an input across these, and the output is going to be A times whatever I apply. And A is going to tend towards infinity. A is going to be huge. Okay, and specific values for A might be 100,000 or a million or things of that sort. Okay, huge A in this abstract amplifier. In addition to that, what's going to have the other properties are that it's going to have infinite input resistance, infinite that means looking in, this looks like an open circuit. Okay, so the fact that this is open here implies the infinite input resistance across these two, across this port. What about the output here? So this is remember this is a voltage source, okay, and we have a 0 output resistance, which means that no matter how the load affects this, as I apply a load, this is going to behave like an ideal voltage source and keep holding the voltage constant based on whatever the function I establish here. And A is virtually infinite. Okay, so let me pause there for a few seconds and just dwell on this so you just understand what the basic device is. Okay, following this basic definition, I'm just going to build a whole bunch of fun little circuits, and the analysis will be pretty straightforward. But this is a big conceptual leap here where there is some circuitry inside it containing resistors, MOSFETs, a whole bunch of stuff in there. I'm not telling you what's inside it. Okay? Much like I could build an abstract amplifier, I could put an abstract box around the amplifier you saw earlier. I'm going to put a box around some circuitry. Okay? I'm not telling you what the circuitry is. And if you are curious, you should look at page 581 of your course notes. And there's an example solved. The example is for a differential amplifier. Okay? This is the small signal analysis chapter. That differential amplifier that's solved in that example is usually the first stage in an operational amplifier circuit. Okay, that differential amplifier is usually the first stage at the input. Okay, and that differential amplifier, as the name implies, amplifies not a single voltage, but amplifies a differential voltage. Note that this guy amplifies the voltage difference between these two terminals. Okay, that's V here. And V is simply the same as V plus minus V minus. Okay, it's the voltage here, the node voltage here, minus the node voltage here. That's what's amplified. So it amplifies a difference. Therefore, it's called a difference amplifier or a differential amplifier. And it amplifies, so that input stage is what's inside the op-amp. Okay, it's got a bunch of other circuitry like level shifters and so on. And at the output, it's got a buffer. Okay, and at the output, it has something that is reminiscent of the source follower circuit that you learned about in recitations, a solved example in the course notes, and in your homework as well. And you saw a variant of the source follower on your quiz as well in problem 2. So a circuit that looks like that appears at the output. Remember, for the source follower, the resistance looking in from the output was very, very small. So you have seen some of the pieces that go inside the amplifier, but we will deal with this as this building block and simply represent it using this little abstract little circuit. To dwell on this a little longer, this little device here is the workhorse of the analog industry. Okay? Much like your primitive gate abstraction, okay, your inverter and NAND gate and so on, much as your primitive inverter or NAND gate was, formed the foundations of the digital industry. Remember, we learned how to build this little abstract device called a NAND gate or an inverter. And we noticed that those formed the foundations of very complicated microprocessors. Okay? So those were the building blocks of the digital industry. In the same way, this little beast here is the building block of the analog industry. Okay? Just to give you an analogy from software, think of this abstract little device as a library routine from a library of functions when you program in C++ or whatever. Can someone give me an example of an incredibly popular routine that we use all the time? That may be called the workhorse of the software industry? Pardon? An abstraction, an abstract procedure. So one example might be something like a printf. Okay? So printf is an abstract name for a procedure that goes and does something for you. Okay? And it's amazing, how we take the printf, the lowly printf for granted. Okay? I stick my printf into my program and include the standard I/O library. It goes and prints a value. You won't believe how complicated the printf is. Okay? As you go into learning more advanced software subjects, implementing the printf is a nightmare. Okay? It's horrendously complicated. Just imagine, you give it a string, okay, and it has to go and print that on your terminal, okay, or on your Windows system or whatever. Think of the complicated steps it has to go through. But as far as you're concerned, it's simple. Just printf something, you're done. Okay? The same way. Okay? Think of this as the printf of the analog business. Okay? It's really simple, and the analysis is going to be incredibly simple. It'll be mind-bogglingly simple. Okay? But inside it, heavens forbid if you look inside it. Tell you what, go into stdio. One of the library routines and just pour through printf. The world's worst horrendous macros are in there. It's just nasty. Okay, same way inside the op-amp. It's nasty. You don't want to go there. So much like in your C programming classes, you were able to use printf without fully knowing how it was implemented. Okay, probably some MIT god or some key graduate implemented it. But once it was implemented, you just used it based on some simple abstract rules as to how it behaved. You didn't have to know what was inside it to use it. In the same way, the operational amplifier. Okay, so just think of printf when you see this, and just imagine how simple it's going to be to use it. Okay? So you may think that I spend way too much time, 10 minutes dwelling on this abstract concept, but I like to dwell on things that I think are incredibly important. Okay, the concept of abstraction is very important, and it's not just in software. The concept of abstraction pervades all of EECS. Okay, and if I were to give you a project to say, okay, go and ask every professor, what is the one word that you think best describes all of EECS? Okay, just pick one word. Okay, go ask every single professor you know. What is a single word that, if you were to characterize all of EECS with one word, okay, what might that word be? Okay, in my mind, it's the A word. Abstraction. Okay, it's all over. If you do a grep on all the words used by all professors in your 4 years here, okay, I promise you, I promise you, the first one will be no, and the second one will be abstraction. Okay, and so check it out. See if I'm, see if what I'm saying is true or not. It's all over the place. In 6001, okay, how many times do you think the word abstraction was used in 6001? It's all over the map. I mean, it's the A word all over. Okay, so imagine you're shocked when you see it being used in 002 because the same concept applies. We build more complicated systems by abstracting out the details of lesser objects, okay, and then using those to build the more complicated systems. Okay, abstraction is it's a very powerful mechanism of dealing with complexity. Okay, so the next step is, how do I go about using the op-amp? So let me show you how it looks on a scope. So what I'm going to do is apply the input to the op-amp. I'm going to look at the output, place the resistor RL to ground, and look at the output. And here, I'm going to apply a plus Vs, and out here, a minus Vs. Okay, and again, remember that a plus Vs simply looks like this, and a minus Vs simply looks like this. Okay, so it's just a inverted Vs applied here, so I get a minus Vs at this input. So first of all, what I'd like to do is, as I change V in, I want to plot for you how V out looks. V in, and this is VO. Okay, I'm going to plot V in terms of microvolts, and VO in volts. Okay, V in is going to have a very, very small, the scale is going to be in microvolts because, remember, the gain of this is huge. Okay, it's on the order of 10 to the 6. It's huge. So small changes in V in are going to cause massive changes in VO. Okay, so I have a very fine scale on the x-axis. So what's going to happen? If I somehow magically make V in exactly 0, if I short these two terminals, okay, if this were a completely ideal op-amp, which it never is, if it's a completely ideal op-amp, then my output should be 0. So as I increase my V in, the output should be A times V in. So for some small value of V in, let's say 1 microvolt, the output should be 1 volt. Okay, so A is a constant, so this will look like a straight line. And let's say my supply voltages are 12 volts and minus 12 volts. If this was an ideal amplifier and I didn't have to worry about the supply, this would just go on extending forever. But I have a plus 12 volt supply and a minus 12 volt supply, so my output cannot go past those limits, and so therefore my output kind of flattens out at these 2 points, and it's called hitting the rails. Okay, so output goes up, and you hear a thunk sound, and you hit the rails. Okay, when you play with op-amps in your next lab, if you listen really, really carefully, you may hear it. Okay, so this saturates out. Not surprisingly, this region where the output saturates at the supply is called the saturation region. And remember, don't confuse it with, it's not the same as your saturation in the MOSFET. It's a totally different thing. It's just happenstance that we call the saturation. Okay, and if you like to think about it, you can think of it as the thunk region. Okay, so that's probably more appropriate and to distinguish it from the saturation region in the MOSFET. Not surprisingly, this one's called the active region. Okay, and it's in this region that we use the op-amp. Here it's hit the rails. Okay, hit the rails and it's kind of dangling out there. It's not much use to us. Okay, so it's in this active region that we use it because this is where the gain is seen. Now it turns out that it's a very high gain device. It's very skittish. Okay, this gain is kind of a really funny thing. It's dependent on a bunch of factors. This could be temperature dependent. This gain here and this curve, it's completely skittish. It could depend on temperature. It could depend on time of day. It could depend on what medications this amplifier is on. It could depend on its mood swings. Who knows what? Okay, this is highly it's kind of unstable. Okay, and A in particular is highly unstable. It's going to be big. It's going to be big, that's for sure. But it could be 10 to the 6. On a rainy day, it might be 2 times 10 to the 6. Okay, if it's feeling sleepy, it may be 0.5 times 10 to the 6. It's big, but I can't rely on it. Okay, so let me show you an example. I'm going to show you this curve for this MOSFET, applying an input and plotting the output. And what I'll do is take a look at this curve. And then what I'm going to do is use a heat gun to heat the op-amp. Okay, and you're going to see this, vary all over the map. Okay, if you still remember last week, some of you may remember that from someplace in a similar situation. Okay, where the GM for the MOSFETs you were given was also dependent on temperature and stuff like that. It's a very common occurrence. Okay, and that's certainly the case for the MOSFET. So let's apply an input and start that again? Okay, so let's do this. So this is this is V in versus V out for the amplifier. Notice that this is plus 12 volts. This is minus 12 volts. It's about 2 volts per division. This axis here is in microvolts, I believe. So for a very small change, for a few tens of microvolts, I have an incredibly high gain. Notice that this has an incredibly high gain here. Okay, the gain is the slope of this line. Okay, it's almost a vertical line. Okay, what I'm going to do next is to have some fun. I am going to heat the op-amp. Okay, and to show you that A is kind of really skittish, and also the fact that it doesn't quite hit 0, it does all kinds of weird things. I'm going to heat the op-amp, and then let's take a look at how that curve fluctuates. Okay, go for it. Okay, we can start. Okay, we can stop that. Okay. So what you saw there was that the op-amp began to behave really weirdly as I heated it. Okay, instead of doing this, it sometimes did this. Okay, it did really weirdly, so getting an offset from the center and so on. And it does a bunch of other things. Can we turn that off? It does a bunch of other weird things, but we won't go into those details. It's not relevant for this course. But the point is that the gain and the offset at the input are dependent on temperature. And we'll look for ways to make it less dependent on temperature. Okay, so as the next step, what I'd like to do is build a circuit. Okay, this is the moral equivalent of your Hello World program. Okay, we're going to use the printf and build a small program on the printf. Okay, you don't have to worry about how printf is implemented, just that we can build horrendously interesting very highly interesting circuits with this horrendously complicated function based on a simple abstraction of the device. So the circuit we will build is called a non-inverting amplifier. Okay? And so from now on, I'm not going to show you the plus minus Vs. I'm not going to show you the power port, but it's in there. Okay, it's hidden under the abstraction layer. So this is my op amp, and I'm going to build the following circuit. So this is my V plus, and this is my V minus. And what I'm going to do is to the V plus, I should apply a V in. Okay? Let me talk a little bit about ground as well. Ground is commonly taken as the point at which I connect my Vs and minus Vs supply. It's kind of at the midpoint. Okay? And if Vs and minus Vs are very carefully tuned, then the output is also going to be at that same ground reference when the input is 0. So the ground is defined as the point at which I connect my plus minus Vs supplies. So I apply my V in out here, and then what I'm going to do, here's my output VO. I'm going to have a resistive divider to ground here, and label these R1 and R2. Okay, and what I'm going to do here is feed this back to the input, okay, to the V minus input. Okay, I'm going to take the voltage, sample the voltage here, and feed that into here. Okay, so this is my abstract model. Okay, and this is my printf. This is my hello world program. Okay, and what we're going to do is simply analyze how this little program behaves. So my equivalent, the way to analyze these is, after one or two simple examples, you will be able to directly analyze this just by looking at it by inspection. Okay? But much as we did for the other pieces, let me grunge through drawing the equivalent circuit and grinding through the analysis. Okay, and then show you the much simpler way of doing it. And even here, even with this grinding analysis, it's going to be pretty simple in any case. So I'll replace the op amp with its equivalent circuit model. Its equivalent circuit was V plus, V minus. So that was the equivalent circuit model of the operational amplifier, just this piece. Okay, so I draw that for you. And then what I'm going to do is I connect my V in here. And remember, I have an R1, R2 resistive divider here. And this one gets connected to this terminal there. I also know that I plus is 0. I also know that I minus is 0. Okay, all I've done is simply replace the amplifier with its equivalent circuit. So let's go ahead and analyze that circuit now. Let's go ahead and analyze that circuit, and it's going to be pretty simple actually. And what I'm going to show you is the hard way of doing it. Okay, I'll show you a much easier way. But the hard way itself is pathetically easy, all right? So what I want to do is find VO in terms of V in. I want to find VO in terms of V in, okay? And there'll be a bunch of other factors thrown in, including things like R1 and R2A and stuff like that. So let's go and analyze it. So VO, well, let's look at that circuit. By the way, let me take 30 seconds and make a little speech at this point. When you see circuits like this, okay, and I saw this happen in quiz 2 as well, for some reason, when you see a new kind of circuit, okay, don't completely, go berserk or freeze or whatever. Okay, there's just no reason to. You know the node method. Okay, the node method is the workhorse of our business. When in doubt, apply the node method. It will simply work. Okay, don't freeze. Don't have to think, oh man, I need to apply a pattern that I know already. I must have seen this somewhere. When in doubt, boom, apply the node method. Okay, so this circuit here, all I have here is one unknown node voltage. I know the voltage is V plus. Okay, I know the voltage, I need to compute the voltage V naught. Okay, and the second, so there are two unknowns. V naught is an unknown, and the voltage here at V minus is another unknown. Okay, so you should be able to, so this is a very simple circuit involving a dependent voltage control voltage source, and you need to find out V naught and V minus using the node method. Just apply it, it's simple. Okay, don't freeze, just look at it and say, I can do it, and apply the node method. It will simply work. All right, so let's do that. So what I can do here is V naught is A times V plus minus V minus. It's actually really simple. And then if I take V plus here, I know V plus is simply V in, so I'll just make that substitution right away. So V plus is simply V in. What is V minus? V minus here is V naught Okay, so what is V plus? I'm sorry, V minus. V minus is simply the voltage that is between R1 and R2. Notice that no current flows into the V minus node. Okay, there's no current flowing in. Okay, so voltage at V minus is simply the voltage given by the resistive divider, which is V naught times R2 divided by R1 plus R2. Okay, let's stare at that for another second. The voltage at this node here is simply given by the resistive divider because no current is flowing in this direction. And no current flows in because I'm telling you there's no current there based on my abstraction. I'm telling you I minus is 0. Okay, so that voltage is simply the voltage at this resistive divider. And so I can simplify it further and write this as V naught. So I get, there's a 1 here. And I move this thing over to this side. So I get 1 plus A times R2 divided by R1 plus R2. And that's equal to A V in. Okay, and simplifying it some more, I get V naught is A V in divided by 1 plus A R2 divided by R1 plus R2. Okay, notice how simple this is, and this is the hard method. Okay, so all I've done is analyze the circuit using basic circuit analysis principle that you learned in the first week of the course, and I have the output for you. And just noted very carefully what the relationships were between the various elements in the abstraction. But notice here that I'm told that A is extremely large. A is on the order of 10 to the 6 and so on. Okay? And suppose it is the case that, let me write that down again. So V naught is A V in 1 plus A R2 R2. Okay, suppose R1 and R2 are more or less comparable, and A is 10 to the 6. It's a huge number. So that this whole number is much, much, much greater than 1. Okay, if it's much huger than 1, what I can do is I can then write this as follows. I can say that, let me do it on this side. So I can say that this is more or less equal to A V in divided by A R2 divided by R1 plus R2. Okay, I'm ignoring the 1 here. As soon as I do that, notice I can cancel out A, and I get V naught to be approximately equal to V in times R1 plus R2, R2. So notice now that when the gain is very large, the output is a function of the input multiplied by some number. The beauty of this thing here is that when A is very large, or this expression is very large, A cancels out, and there's no A in this relationship. This means that even though the basic amplifier was very skittish, the output here relates to the input based on components that I have control over. Okay? These are soldiers in my army. Okay, I control them. So to give you a sense of some numbers here, suppose A was 10 to the 6th, and I choose R1 to be 9R, and R to be some R, then V naught is 10 to the 6th V in divided by 1 plus 10 to the 6th R divided by 9R plus R. Okay, so that's 10 to the 6th V in divided by 1 plus 10 to the 6th divided by 10. All right? So notice that, so if I ignore the 1 here, the 10 to the 6th and 10 to the 6th cancel out. This ends up giving me 10 V in. So I get a really nice amplifier whose output is simply 10 times the input and determined solely by some resistor values. Okay, let me show you another quick demo this time and show you the amplifier again, but with the resistors connected like that. And then I'll show you that I want to heat the amplifier to the wazoo, the op amp to the wazoo, but V naught is going to be absolutely rock solid. Okay? Let's try that out. So so this time around, this is the transfer function, the V naught versus V in. And notice that this time around, I have similar scales on the X and Y axes, and this has a slope of 10. Okay, this is the point where the amplifier saturates at plus 12 volts, and this is minus 12 volts. And this point here is the 0. So this is V in, V out, plus 12, minus 12. And this slope is 10. So what I'm going to do now is heat the op amp to the wazoo, and this ain't going to change. Okay, because it's my external resistors that control it, independent of the value of A, provided A continues to be very large. Yeah. Okay, so I'm just articulating the V out, V in curve. And let me start heating the op amp. So notice that it's pretty stable. Okay, it doesn't change because it's independent of the amplifier values. Okay? So what I've done now is by connecting these resistors in this way, I have a nice amplifier with a gain of 10. But the question you may ask yourselves is, why? There's a little sucker in there that wants to shoot things up by 10 to the 6th. Okay, wants to knock things off to one rail or the negative rail. So why is it that it's behaving like a docile lamb here and giving us a nice little factor of 10 gain no matter what I do to it? Why is it doing that? What's the intuition behind it? Okay, I'll draw something on the board, but for the next 10 seconds, I want you to think about it. See if you can come up with some insight as to why is it doing that? I mean, why is it exactly 10? Why not, why isn't that 10 to the 6 kind of killing me somehow? Okay, why am I getting exactly 10 no matter what happens? Okay, see if you can come up with some intuition, and then I'll show you how it works. I'll redraw the circuit in the meantime. Okay, so let me see if I can give you some intuition. So let's say this is my circuit, and let's say this is R and this is R. As an example, let's assume that the input is 5 volts. V in is 5 volts. Okay? So if R and R are equal, what should the output be? It's R and R, so it's R1 plus R2 divided by R2, right? So it's 2R divided by R, so it has a gain of 2. So my amplifier has a gain of 2 because R1 plus R2 divided by R2, which is my gain, is R plus R divided by R equals 2. So this will be 10 volts. If that is 10 volts, this is going to be 5 volts, correct? Okay, this R and R, voltage divider, this is 5. So I get 5 volts here. So this is V plus, this is V minus. So I get R and R, 5 volts here. That's how the circuit looks. Okay, now let's understand what's going on. Okay, and listen very carefully. This is going to be a key insight that I hope you will carry with you for the rest of your lives. This is really, really key. Okay, what you're about to see is, I think, the third big aha moment in 6002. Okay, like small signal analysis, like the frequency domain stuff we saw. I think this is the third big one. Okay, in the next 30 or 40 seconds. Okay? Things that are completely, not necessarily intuitive, but are just spectacular in terms of what they can do for you. So let's suppose that because I'm heating it, okay, let's suppose that A suddenly tends to increase. It wants to increase because I've heated it. A is saying, I want to get out of this mold here, and it's trying to break through its shackles here. Okay, so let's say, as a Gedanken experiment, that it tries to shoot up this to 12 volts. It tries to push it up higher. Okay, this is just a Gedanken experiment. So the up arrow says that the increase in A is trying to push up V0 momentarily. Let's see what happens. So it's trying to push up V0 momentarily. So let's say this goes to 12. Okay, hypothetically. If that goes to 12, what should this node go to? 6, exactly. So this goes to 6 volts. If that goes to 6, what does V minus go to? 6 volts again. So V minus goes to 6 volts. Now at the input I have 5 volts at V plus and 6 volts at V minus. So where should the output go? Output should go down. So because this is, the voltage at the negative terminal is higher, and so the output is A times V plus minus V minus. And because this has gone down, and this has gone up here, it's going to try to pull the output down. So that's going to pull the output down. Okay, let's say to 9 volts or something. Okay, ka-chunk. So there's a big battle going on here. A has gone up, it's trying to boost it up to 12. But the moment that goes to 12, this goes to 6, this goes to 6, and the op-amp output tries to go down to 9 volts now because this input is higher here. If this goes to 9, this goes to 4.5. If that goes to 4.5, this goes to 4.5. What happens now? If this goes to 4.5, what happens? It wants to go back up. Can it make up its mind? So this guy wants to go back up now because V plus is higher than V minus. So what are you seeing here? This whole circuit here behaves like my little son. Okay, my 9-year-old. If I say do this, he wants to do the exact opposite. Okay, so there's a trick in how you make them do things for you. So look at this. So because of this arrangement of the circuit, when A tries to push the output up, the rest of the circuit tries to pull it back down to where it used to be. Okay, so if the circuit tries not to follow the true path, the rest of the circuit tries to whack it into shape so it follows the true path. And what's happening is because I've fed back, in this arrangement, I've fed back a portion of the output to the negative input. Okay, I have fed back some of the output to the negative input, and by providing this feedback, of a portion of the output to the negative input, I've arranged it in a way that I have something called negative feedback. Okay, what negative feedback does is that if this wanted to go wild and crazy, the circuit provides it with some negative feedback, like you just saw. Okay, feedback, a big word. Okay, if you take a poll of all the EECS faculty, I suspect that feedback will rank at least as the 9th or 10th most important word in EECS. Okay, if abstraction is number 1, I think this would rank like a 9 or a 10 or something. Okay, so that's the reason why it worked. In the last couple of minutes, let me give you some insight based on something that you know on how feedback works. So this is a road here. And let's say, let's look at anti-lock brakes. Okay, so this is my tire. And let's say I have a set of disc brakes here. And as the car is moving forward, if I apply the brakes, the tire stops rolling. But if I apply the brakes too hard, it can lock up the tire and the whole car can skid. Okay, the way anti-lock brakes work is as follows. There's a controller that sits here, and there is a little person looking at the wheel and seeing, is it turning? So this is the feedback. And it's saying, is it turning? Yes. Or is it not turning? No. Okay, all this person watching the tire is doing is saying, is it turning or is it not turning? That's it. That's a feedback path. It's a negative feedback. And so if it's no and if it's yes. If it's yes, then what this does is it applies the brakes even more strongly. It's turning, so I can pump more, apply more brakes. But if it says, oops, it stopped turning, what it does, it simply releases, the controller releases the brakes. Okay, and as soon as the controller releases the brakes, this one tends to loosen up a little bit, the tire starts turning again. So this way you're constantly keeping the tire in its region of critical friction so that it's constantly moving, and static friction applies to how hard you can brake. Okay, and it doesn't start skidding. So in fact, if you take your car out, let's say I don't say you do this, but let's say you go onto the Charles River in the dead of winter, and you drive on the lake, and you slam your anti-lock brakes on, okay, or on an icy patch, you will notice that there is a constant, sound that looks like something is vibrating in there. Okay, that's exactly what is happening. Oops, the tire's locked. Release the brakes. Release the brakes. Oh, okay, wheel's turning. Okay, jam the brakes on. Okay, that's exactly what is happening. Same way as out there, you notice that, oops, the output's going up, pull it down. Oops, it's going down, pull it up. So there's constant feedback, negative feedback, that is keeping the output stable. Okay, very important concept, and I'll ask your recitation instructors to cover the very simple method that is on page 9.